scattered throughout the centers of almost every galaxy are infinitesimal dots of inescapable darkness. When a massive star dies, its core stops pushing outward and begins collapsing inward, leaving behind a point of gravity so intense nothing can return. Albert Einstein, whose equations predicted these objects, initially believed they were a mathematical impossibility, an abomination that nature would never permit to exist in reality. But the formation trigger is a simple matter of fuel. A massive star eventually exhausts the nuclear hydrogen in its core, losing the internal pressure required to support its own immense weight. Without that outward pressure, the star's entire mass is condensed by gravity into a single point. It becomes so dense that it literally punches a hole in the fabric of space-time. This death of a massive star produces an object behaving like nothing else in the cosmos, creating a region of space that we are only just beginning to map. If a black hole traps all light, it should be impossible to see, yet astronomers have spent decades tracking and measuring them. We detect them by looking at the accretion disk, a ring of gas and debris spinning at extreme speeds around the central void. The intense friction heats the falling material to millions of degrees, making it glow brightly enough to be seen across billions of light years. To see this in our own galaxy, scientists use the Event Horizon Telescope, a global network of radio observatories like the VLA shown here. In 2022, they captured the shadow of Sagittarius A star, a supermassive black hole located 26,000 light-years away at the heart of the Milky Way. By photographing that shadow, astronomers moved black holes from the realm of mathematical curiosity to observable physical reality. If you were to descend toward that shadow, the fundamental rules of time would begin to distort. This is gravitational time dilation. Einstein's theory of relativity shows that extreme gravity causes time to pass slower for someone near the source compared to a distant observer. To an outside observer watching you fall, your movements would appear to slow down. You would seem to turn red because the light waves you emit are being stretched by gravity, a process called gravitational redshift, until you eventually appear to freeze at the edge forever. But for you, the traveler, time continues to tick normally. You would simply plunge forward, feeling no change in the pace of your own life. You eventually reach the event horizon. This is the ultimate physical boundary, where the gravity is so high that the velocity required to escape is greater than the speed of light. Once you cross this horizon, you are permanently severed from the rest of the universe. Your journey becomes a strictly one-way path into the center. As you get closer to the mass, tidal forces take over, leading to a phenomenon known as spaghettification. This occurs because the gravitational pull at your feet is exponentially stronger than the pull at your head. This difference in gravity stretches matter vertically into a long, thin string, while simultaneously compressing it from the sides. Surprisingly, the danger depends on the size of the black hole. If you fall into a small, stellar mass black hole, these forces will rip you apart long before you even reach the event horizon. But a supermassive black hole, like Sagittarius A star, has a much gentler curvature at its boundary. You could cross the horizon of a giant black hole perfectly intact. While the supermassive black hole spares you at the entrance, it only delays the physical destruction that awaits you deep inside. Once you are inside the event horizon, the dimensions of space and time effectively swap roles. The singularity at the center, a point of infinite density where math breaks down, is no longer a place you can avoid. It becomes a moment in your future, as inevitable as tomorrow morning. In 1974, Stephen Hawking discovered that black holes are not permanent. They slowly leak energy and evaporate over trillions of years through Hawking radiation. This leads to the information paradox. If everything falling inside is destroyed and evaporated, it would violate the quantum law that says information cannot be lost. Because our current understanding of physics stops working at the singularity, scientists are looking for answers in theories that challenge our traditional view of reality. One theory suggests the singularity is actually a wormhole connecting two distant points in spacetime. Instead of being crushed into a point, matter might bounce outward on the other side, potentially seeding a new universe. These objects teach us that space can be crumpled like paper, and time can be extinguished. They suggest that the sacred laws of physics we rely on may only be localized rules, waiting to be rewritten at the next cosmic threshold.